Continuing with our lesson on the subject of amines, let's take up the Hoffman elimination next. In this reaction, we exhaustively methylate an amine. In this example, it's a primary amine, but it could be a secondary amine. And you can see that we've replaced both of the hydrogens and we've added an additional methyl group on this nitrogen. It now carries a plus charge. Then we add silver oxide. Okay, what this does is it precipitates silver iodide, and it replaces the iodide anion with a hydroxide. Okay, if we heat this, this will undergo an E2 elimination, where trimethylamine is the leaving group. Okay, this is the exhaustive methylation reaction. We use excess iodomethane, and then we convert the iodide salt to quaternary ammonium hydroxide salt. And then when we heat this quaternary salt undergoes an E2 elimination, and we get an alkene and a tertiary amine. The Hoffman elimination is regioselective. Okay, in 2-butanamine, we actually have two sets of beta hydrogens, those on 1 and those on carbon number 3. So there's two possible alkenes that can be formed. Last semester we talked about the Zaitsev product, Zaitsev's rule, which says that the more substituted alkene is favored. Now with the Hoffman elimination, it's actually the less substituted alkene which is favored. So 1-butene is produced in 95% yield, whereas 2-butene is only produced in 5%. The hydrogen and the leaving group have to be anti to each other, 180 degrees apart in the same plane. And okay, so it's possible you can get stereo selectivity as well. Okay, let's take a look at the Hoffman elimination for this secondary amine. Okay, we have 3 different sets of beta hydrogens. We have the methyl group here. This is alpha, this is beta, so we have beta hydrogens on carbon number 1. We also have beta hydrogens on carbon number 3. Okay, so we could get an alkene here, we could get an alkene here, or we could get an alkene here. And those are illustrated using the red arrows, the blue arrows, and the green arrows. In all 3 cases, in all 3 cases, a tertiary amine is formed. Okay, so this amine would be formed following the pathway of the green arrows. This one with the blue arrows, this was the red. Okay, since ethylene is the least substituted alkene, we would predict that it would be the major product, and in fact it is. Amines are readily oxidized, and these are some of the oxidation products. We can get hydroxylamines, amine N oxides, nitroso and nitro compounds. Amines are easily oxidized even in air. A good example of this is aniline. Pure aniline is a colorless liquid, but when it's been exposed to the air for any period of time, it can turn a dark brown color. Okay, sometimes oxidation reactions are desirable, and when that's the case, common oxidizing agents include hydrogen peroxide and MCPBA. Secondary amines can be oxidized to hydroxylamine. Tertiary amines are oxidized to amine oxides. Okay, so here's an example of preparation of an amine oxide from a tertiary amine. Okay, notice the nitrogen carries a plus charge and the oxygen carries a negative charge. This reaction takes place readily. It gives good yields. One of the reasons for preparing an amine N oxide is to do the Cope rearrangement, also called the Cope elimination. Okay, this is an E2 elimination where the negatively charged oxygen removes a proton, we form the double bond, and then in this example, dimethyl hydroxylamine is eliminated, and we get our alkene. Okay, this is an E2 mechanism, and just like with the Hoffman rearrangement, or the Hoffman elimination, I should say, this will favor the least substituted alkene. Okay, an advantage of using the Cope rearrangement is that we don't have to use a strong base. The amine oxide acts as its own base. Okay, so what would be the expected products from the Cope elimination? Okay, here's our nitrogen, our alpha carbon and our beta carbon. We also have a beta carbon going this way. So there would be two possible alkene products, one inside the ring and one outside the ring. Okay, so if the negatively charged oxygen removes this beta hydrogen, we form the alkene here, and then we eliminate the dimethyl hydroxylamine. This is a minor product. The major product is actually the methylene cyclopentene. It's the less substituted. Okay, next we'll look at the topic of diazonium salts. Diazonium salts can be prepared from primary amines when they react with nitrous acid. Nitrous acid is unstable, it's not commercially available, and so we prepare it as we need it by treating a nitrite salt like sodium nitrite with a strong acid like hydrochloric acid. These diazonium salts are unstable. They'll decompose and form carbocations and nitrogen. This is the mechanism for formation of a diazonium salt from an amine. Okay, I won't spend a lot of time on this. Okay, alkyl diazonium salts like methyl or ethyl are very unstable. They immediately lose nitrogen. Arene diazonium salts have a longer lifetime, and in fact, they are useful intermediates for a number of different reactions. Okay, for example, we could start with toluene. We could nitrate it. We could reduce the nitro group, say with iron and HCl, followed by hydroxide, to the primary aromatic amine. Okay, then we can generate nitrous acid using sodium nitrite and HCl, and that produces the diazonium salt. And then there are various reagents that we can use to replace that diazonium group. We have one of the very best leaving groups there is, and that's nitrogen gas. Okay, I've got a couple of different slides here that show some of the different reactions that we can run. Okay, so we've generated a diazonium group. We can use, for example, copper 1 chloride to produce the chlorobenzene, copper 1 bromide, and copper 1 cyanide to produce the benzonitrile. This one, and this one are collectively known as the Sandmeyer reaction. They involve a copper 1 salt, and the reaction appears to be more complicated than simple substitution. There's a redox reaction going on between copper 1 and copper 2. Now, in the case of iodine, it's not necessary to use copper 1 iodide because iodide is a good enough nucleophile where it can displace the diazonium group. Let's go back up again. Okay, some other reactions. If we were to react the diazonium group with tetrafluoroboric acid, HBF4, and heat it, we could get an alkyl fluoride. Okay, if you think back to our chapter on aromatic substitution, we didn't have a way of producing aromatic fluorides. Aromatic fluorides are actually very useful in drug synthesis. All right, if we heat our diazonium salt with dilute acid, say water and sulfuric acid, we can replace this diazonium group with a hydroxyl group. We get a phenol. Okay, and again, we didn't have a good way of producing a phenol by electrophilic substitution. Okay, this reaction involves a reagent called hypophosphorus acid. It's H3PO2. And notice what this does. It completely removes the diazonium group and replaces it with a hydrogen. Okay, there are some times where this is actually useful. If we want to make use of the orthopara-directing effect of an aniline or the meta-directing effect of a nitro group, and then ultimately convert it to a diazonium, and then we could remove that group when it's no longer needed. Okay, and the last example of a reaction involving a diazonium group is if we have a strongly activated aromatic ring. Really the only two things that are activating enough to form this coupled diazonium compound would be phenols and aromatic amines. Okay, it has to be a strongly activated aromatic amine. Here, the diazonium group is not acting as a leaving group, but it's acting as a very weak electrophile. And so that's why we have to have a very strongly activated ring. Okay, this is the Sandmeyer reaction, in which the diazonium group is replaced by chlorine, bromine, or cyanide. Treating a secondary amine with the nitrosonium ion, which is generated from nitrous acid, produces a nitrosamine. Nitrosamines are stable, but they have been shown to be carcinogenic in lab animals. Right, in our next lesson, we'll be looking at preparing amines by reductive methods.